we know that the most common form of a linear equation is y is equal to mx plus c, but for quadratic equations, there's actually a wider range of them, and that's just because we have more numbers involved in our quadratic equation, and it allows for more variation in what forms we can put our quadratic equation in. Now, the most common one that we see whenever we're talking about quadratic equations is the expanded form, y is equal to ax squared plus bx plus c. And it's very obvious why this is the most common one. It's because it illustrates each of our terms that build up our quadratic equation very clearly. So you have your x squared term, or we call that the leading term usually for polynomials. So this is what causes it to be a quadratic. If this term didn't exist, then we'll just have bx plus c, which is pretty much just a linear equation. So that's why this one you could argue is the most important, and that gives us a lot of our features that we recognize with quadratic equations. And then you have your coefficient of x, which does something different, and then you have your c value, which does something different as well. Now, the reason why we have so many forms is because they all tell us different pieces of information, and that's why they're all labeled different things. So you have expanded form, which is pretty standard, and then you have your factorized form, which is a different form, and then you have turning point form, which is arguably the most unique. So expanded form tells us something specifically, and they all say different things. So one of the main things that it says is the a value. I just want to clarify before I continue that you can get all of the numbers that you need to know for a quadratic equation from all of these forms, but then some of them are given directly, and that's what I'm going to talk about, and then the rest you can get indirectly, okay? So we don't want to just say, okay, this form is the best because it gives us the most piece of information. You can get all pieces of information from all of these forms, but it's just easier to get some piece of information from one form and then other pieces of information from other forms. So all of them have the a value here, and they all do the same thing. It all tells us what we call dilation and what we call the reflection as well. So pretty much, if you have this a value here and it has a larger value, we say that it has a higher dilation from the x-axis. I'm going to cover this in the transformations unit anyway, so it doesn't really matter. Just know that this a value can change, and that'll change the stretch or how wide the parabola is. So if you have a larger a value here, you get a more narrow parabola. If you have a smaller a value in magnitude, let's say you have 0.2 or something like that, then you're going to get a much wider parabola. Also, if you have a negative a value, it causes the parabola to be upside down, and if you have a positive a value, it causes the parabola to be the right way up, or like a positive parabola, we call it. Now, that's what the a value does, but the most important term that's unique to this one is this c term here. The c is the same as our c in our linear form, which is the y-intercept. So c is equal to the y-intercept. And we can read that off the equation directly, so there's no extra calculations that we actually need to do. And that's the main thing that comes from the expanded form directly. There's other things, as I said, that you can get indirectly, but if you want to get the x-intercepts, then you go to the next form, which is the factorized form. Now, hopefully you all remember how to get from factorized form to expanded form. There's going to be extra videos in the modules on our online course that goes through all these basic things that are covered in previous years, but aren't really covered in the course that thoroughly because it's kind of assumed knowledge. But obviously, people need a still refresher, and people need to still understand those types of things. So that's why we're slowly building up that part of the course, and it should be ready in a few weeks. And I'm just slowly adding stuff. A lot of the things are like this, expanded versus factorized form. It's also going to be logarithms, surds, indices, like index laws, because those things aren't covered in the course in year 12 because there's bigger fish to fry, you could kind of think of it as. But yeah, people still need help with that type of stuff, so that's why I want to include it in our online coursework. Now, for the factorized form, the most direct thing you can get apart from that a value are these values in the brackets here. So you can see x minus m, x minus n as well. Now, the x-intercepts of our equation or our shape are going to be x is equal to m and x, not y, that's just default reaction, muscle memory. X is equal to m and x is equal to n. So those are the x-intercepts to our equation, and the reason why we have multiple is we know that for a quadratic shape, you can cut through the x-axis twice now, and I'll just give you an example of a shape that would hypothetically have that. Is something like this. So you have one intercept here, one intercept there. Now, this is not always the case. You don't always have two x-intercepts, but it's just know that it's a possibility. You can also have one x-intercept, and you can also have no x-intercepts. And in that case, you wouldn't be able to go into this form here. But if you can read off this form, you can see one number's there, then you have two x-intercepts. But again, it's not always the case. So sometimes you can't actually put something into factorized form and you wouldn't be able to get those x-intercept values because there's not two that exist. It might be 1 or it might be 0. We'll talk about that in a future video. Now, turning point form, pretty self-explanatory what we get from this one. It's the turning point. Now, the turning point of our parabola is probably the most unique feature compared to the linear equations, because linear equations do have x-intercept and y-intercepts both, and they all, most of the time, they have a single one each. Turning point is the new feature that belongs to the quadratic equation. And as I talked about in the intro video, the reason why the turning point actually exists is because of that squared feature or the squared nature of our equation, and that causes you to have either a minimum point, which we talked about in the y is equal to x squared, but if we have an upside down parabola, then we call that our maximum point. Again, we'll go into that in more detail in a later video. But the turning point in this case is going to be h, k. Just note, same for this one here, if you have a minus in there, you take the negative of that so it becomes positive. So that's why I've got x minus h, but then I take positive h in my turning point form. That's just the way the numbers work. It's just something that you have to rote learn for now. And then for the positive k, you just take the absolute value of that, or like the raw value of that. So if it was negative here, you put negative there. If it's positive here, in this case, like it is, then you take the positive k value. So these are the pretty much the only three features that you need to know to sketch a quadratic equation. And these are all features that are necessary too. You can go beyond this if you want to. You can get an anchor point if you want to. But these are the three bare minimum and usually the features that will get you all the marks when you're sketching a quadratic equation. So you can get the y-intercepts from this form, the x-intercepts from this form, and also the turning point form from this form. Pretty self-explanatory for this one. But as I said at the start of the video, you wouldn't convert this equation, let's say if it's in expanded form, you wouldn't convert it to factorize and then convert it to turning point form to get all the features. There's actually shortcuts for getting all of these features from their respective form. So I wouldn't recommend doing that for all features. We'll go through a few examples in the next sort of clip, and that'll teach you, hopefully it'll illustrate the easiest way of getting all the pieces of information from each of our forms that we have here. Now what we're going to do is take each of our forms and get all the pieces of information that we need to sketch our parabola. Now this is going to be really valuable for you because if you ever get a quadratic equation in the form that we're going through, then you can just apply the same process. It's just going to be slightly different depending on the numbers, obviously. So we're going to start off with the expanded form because that's the most common one, and we're going to get the information that we can get from it directly, which remember is y-intercepts from the previous video, and then you can get the x-intercepts indirectly and also the turning point indirectly as well. And we're going to show you the most efficient way for getting them for these forms here. Now the y-intercept is the first easy one. We know it's going to be our c value, which in this case is positive 3. So y is going to equal positive 3. Therefore, our actual coordinate is going to be 0, 3. Don't forget that for y-intercepts, the x value is 0 because it's lying on the y-axis. Now, x-intercepts, we can't read off the form directly, but what we do is we, as you should remember, we factorize our equation here. So we factorize the equation and put it into our two brackets. I don't want to go into detail. I don't want to explain too many details about the expansion form or factorizing from expanded form, but you should remember it, and if you don't, as I said in the previous video, you can watch our modules for those specific things that you need to catch up on. But just as a quick reminder, we want to know what adds up to -4 but multiplies to positive 3, and the only numbers that fulfill that condition are -3 and -1. Therefore, our factorized form is going to look like x minus 3, x minus 1. -3 minus 1 is equal to -4, -3 times -1 is equal to positive 3. Now we're in expanded form, and we can get our x-intercepts from here. So we say x is equal to 1 or 3. Don't forget we have negatives here, and you take the negative of that minus value, or you take whatever value is minus. So you can say 3 is minus there, 1 is minus there. That's why I get positive 1 and positive 3. So if we want to put it in coordinate form, we got positive 1, 0, and then positive 3, 0. Sweet. Now, the last one is the turning point form. What a lot of people, this is the most common mistake that I see people make, or just students make in general. If they see this expanded form and they want to find the turning point, and it makes sense why people do this, they complete the square, which is the process of getting something into turning point form. Now that is a big time waster because completing the square is actually pretty hard. It's not too bad for this equation because the numbers are pretty simple, but let's say if you had a dilation factor on the outside, it would actually make it a lot harder to do that. So a quick shortcut that a lot of people kind of overlook because they don't really think about the things too deeply is the turning point x value is always going to be halfway between the x-intercepts. And if I just say that, it makes sense because our quadratic equation is symmetrical, and what actually happens is that the x-intercepts are going to be equidistant from the x value of the turning point. What I mean by that is if I sketch my points here, so I have 1 here, I have 3 here, I'm kind of trying to keep everything in scale, and then I have my y-intercepts there. So this is I'm just going to write it in coordinate form, 1, 0, this is 3, 0, and then this is relevant for later, 0, 3. If I have x equals 1 and x equals 3 as my x-intercepts, then my turning point is going to be somewhere here, but it's going to lie exactly at x equals 2, because that's halfway in between 1 and 3. So if I want to find the x value of my turning point, and this is what my working out will look like as well, by the way. If I want to find the x value of my turning point, I say that that's going to be 1 plus 3 over 2. Essentially just the median or the average between the two x-intercepts. A very useful feature, the symmetricality of our quadratic equation, because we can get the x value of the turning point straight away. So 1 plus 3 is 4, divided by 2 is x equals 2, and that makes sense if you just look at it 1, 2, 3. 2 is in the middle, 1 and 3 exactly. Now if you want to find the corresponding y value, same as any other equation, doesn't matter if it's quadratic, linear, whatever. If you want to find the y value, you just substitute in the corresponding x value, which we just found here. So we say the y value of our turning point is going to be the substitution of x equals 2 into our equation. So we say 2 squared minus 4 multiplied by 2 plus 3. So we get 2 squared, which is 4, minus 4 times 2, which is 8, plus 3. 4 minus 8 is negative 4, plus 3 becomes negative 1. So my turning point is at 2, negative 1, which makes perfect sense because not only is it in halfway in between 1 and 3, but it's also negative, which makes sense because we're dipping down below the x-axis and then coming back up to reach our other intercepts to continue that trend. So again, trying to keep everything to scale. This point here is going to be 2, negative 1. And these are all the features that we need to sketch our quadratic. So I'm just going to sketch it here, trying to keep my shape, trying to get my curvature. And that's pretty good for whiteboard standard. I'll just label my equation, which is good practice, put arrows on the end of it. It's not an essential thing, but I like to use it to indicate that the graph keeps on going in that trajectory. X is equal to x, y is equal to x squared minus 4x plus 3. And we can see we've ticked off all our features. We've labeled our axes there. You've got x equals 1, x equals 3, which are our two x-intercepts. We've got turning point, which is very clear, and we've got the y-intercept as well. Just one thing to note for this, when sketching these things, a shortcut a lot of people do is they don't put their key features or their key points in, in coordinate form, but they just put the singular number and they assume what the other value is. And that's very fair enough because first of all, a lot of teachers do that. Second of all, the textbook does that a lot as well, which I've noticed in the new version. And it's not good practice because you won't get the marks on a test, like on a SAC or an exam, if you do that. For example, people will just put 3 next to this point here. It's very obvious what it is. It's the y-intercept, but you can't assume that when you're sketching the points or like when your examiner won't assume that when they're marking it, so that's why I put everything in coordinate form. That's why I've got 1, 0 there, 3, 0 there, and then 2, negative 1 there. Everything should be very clear in coordinate form. If you've got x and y intercepts, put them in coordinate form as well. Don't just include the singular values. That's pretty much it for this example, I believe. Yeah, I would say this is pretty good working out as well. In terms of the mark distribution for a sketching question, it's pretty hard to say, but you'd get a lot of your marks for the working out, and then if you get those correct marks for the working out, most of the time the shape looks appropriate. But where a lot of students usually lose marks is the actual shape of the parabola here. Just make sure that has that curvature, and then it goes back up towards positive infinity if it's a positive one, obviously negative infinity if it's a negative one, and just make sure that your graph looks somewhat symmetrical, which this one does. Now for this example, what we have is a factorized quadratic equation, but this one I've made a bit more complex on purpose because I want to show how we deal with these types of issues or these types of complexities with our equation. In this case, I have a factor on the outside of my factorized brackets, and it's -2. So first of all, what does the 2 do to our calculations? And also what does the negative do to our calculations? And also, how do those two features affect our graph? Now, because this is in factorized form, the first thing that I can get directly from this equation form is the x-intercepts, which are in these brackets here. So again, we take whatever value is minus, or the negative of what value is there. So -3, x minus 3 shows us that we have an x-intercept of +3. So we have 3, 0. And then we also have x plus 2 in our bracket there. And what we do is we take the negative of that value. So we have the other x-intercept as -2, comma 0. I remember in the previous video, I didn't actually explain why we take the negative of those values, but I just explained it really quickly with a different color. It's something called the null factor law, and what the null factor law suggests is that if A multiplied by B is 0, just in general, then A must equal 0 or B must equal 0. But algebraically, what we do is, even though we say or, it's like one or the other, but we just take both as solutions that could equal 0, because it's all about possibilities, not definitive outcomes. And that's why for our equation, it's not definitive. It's like it's an equation, and it creates a shape on purpose because we have that variable x. But because we have that variable x, there are multiple values that can cause this equation to be 0, and that in this case is either A or B. But for this example, how we get the negative of each of the values that's in our bracket is because if we have this equation is equal to 0, then this bracket could equal 0, or this bracket could equal 0. So if I just write that here, x minus 3 could equal 0, or x plus 2 could equal 0. Now if x minus 3 equals 0, what we do is we just move the 3 across, so we get x is equal to 3. Now if we have x plus 2 is equal to 0, we move the 2 across and we get x is equal to negative 2. And that's why we take the negative value inside our bracket. But let's just say this is a bit of a tangent, by the way, but it's good to understand what's actually happening. Let's say if our quadratic equation was slightly different. Let's say if it was y is equal to 2x minus 1 outside of x minus 3. Now in this case, x is actually not going to equal 1 as my x-intercept, and that's because 2x minus 1 is equal to 0. Therefore, x is equal to positive 1/2. So what you need to do is take each of our factors that have x inside it, and then you rearrange for x when you let them equal 0. The shortcut is just, if you don't have the coefficient of x in the bracket here, you just take the negative of this value. But the reason for that is because of the null factor law, which I've explained there. So hopefully that makes sense. Hopefully that clarifies things and just explains why. And as I said in the start of this video, or the start of the previous video, if you understand things are why the way they are, then you're most likely not going to forget it. Now for the y-intercept, just in general, y-intercept happens when x is equal to 0. In the expanded form, by default, it's the value on the outside. But in this case, what we do is we don't expand our equation. We just substitute in x is equal to 0 to get our y-intercept. So in this case, what we do is we say y given that x is equal to 0. If you don't know what that symbol is, it's the given symbol, that vertical line. So that notation is just saying substitute x equals 0 and give me the y value pretty much. So negative 2 outside of 0 minus 3. Multiplied with 0 plus 2, so I end up getting negative 2 times negative 3 times positive 2. That becomes positive 6 times 2 is equal to positive 12. So our y-intercept is 0, 12. Now for the turning point, we do the same thing as the previous form. Because we have it in factorized form and we know the x-intercepts already, then we can just find the average of them to find the x turning point. So x of the turning point is going to equal 3 plus negative 2 divided by 2, which becomes 3 minus 2, or 1/2. Now, what we do is we substitute this into the equation, same as previously, to find the corresponding y value. Now, I've chosen these numbers on purpose because it is a bit complicated, but I'm just showing you that the process remains the same. So it becomes negative 2 multiplied with x minus 3, or 1/2 minus 3, multiplied with 1/2 plus 2. So we end up getting negative 2 multiplied with 1/2 minus 3. 3 is the same as 6 on 2, so we end up getting negative 5 on 2 for that fraction. And then 1/2 plus 4 on 2, it becomes positive 5 on 2. The negatives cancel out, and also the 2 cancels out with one of the 2's there. So we end up getting 5 times 5 divided by 2, or 25 over 2. Therefore, my turning point is 1/2 and 25 on 2. Nice. Now, what we have to do is just put all of our information on this Cartesian plane here. So we have positive 3 and negative 2. So I just want to keep it to as in scale as possible. So you can see the 2 obviously goes to the left by a certain amount, and the 3 goes to the right by a bit more. The turning point is close to the x-axis, but it's not quite at the x-axis. It's at 1/2. So it'll be very close though. And also the y value is roughly, it is exactly 12.5. So it's going to be relatively high up. And then for our y-intercept, it's at 0, 12, and that makes sense because my turning point is close to the x-axis. My y-intercept will be not too far away. It'll be relatively close, but it's still really important to include all those features there. I might do a zoom in on the camera just to show that those points both exist. They're very close together, and it's kind of hard to see, which I can imagine, but that's all good. Now, what you can see is that before I even join the shape together, I've got a very narrow shape compared to my previous part of the video where we had no number on the outside. And the reason why this one's so narrow is because of that dilation, we call it, but caused by that 2. The other key difference between the previous parabola and this one is also that we have this negative shape. You can imagine if you join these dots together, you get a negative shape, and that's caused by that negative on the outside on that coefficient of our equation. So let's just sketch this shape, and you can see visually how narrow it is. I kind of missed the y-intercept, but that's okay. So you can see, yep, again, it's very narrow, and it's also that negative shape, which causes the turning point to be our maximal value, not our minimal value if it was positive. This point here is 3, 0. This point here is -2, 0. The y-intercept is 0, 12, and our turning point is 1/2, 25 on 2. Sweet. So that's our quadratic equation done. Again, this we started off in factorized form. To get our y-intercept, just substitute in x = 0. To get our turning point, we just do this previous process as the video before. You take the average of the x-intercepts and you find the corresponding y value. Our last quadratic form is turning point form, and as the name suggests, it gives us a turning point directly in the form that it's in. So in this case, we have y = x - 1 squared minus 4. Now the 1 and the 4 signify our turning points, x and y coordinates, but there's a bit of sign changing when it comes to reading off some of the values. So for example, the x value of our turning point is actually +1. So even though it's a negative number, we take the positive of it. So in this case, it's going to be +1. But let's say if it was x + 1, we take -1 as the x value of our turning point. The reason for that is something to do with the transformations and the order that the transformations are applied in. We don't actually have to know right now. Just know that if it's x - 1, you take the +1. If it's x + 1, you take the -1. The outside number though, we actually don't change the sign. So it's -4 on the outside. So your y turning point is -4. So this is the turning point of our quadratic equation, 1, -4. Now our y-intercept, what we do is we let x = 0, and it's just your usual, when x = 0, you get your y-intercept. It's not the value on the outside, don't confuse that, because if you have expanded form, yes, if you the y-intercept would be the value on the outside, but because this is in turning point form, the value on the outside represents the y value of the turning point. So what we do is we say y = 0 - 1 squared minus 4. So 0 - 1 is -1, squared becomes +1, minus 4 is equal to -3. So we have 0, -3. Now for our x-intercepts, what we could do is, there's actually a couple of ways that we can do this. One way is letting y = 0 and then rearranging for x. So we'll do that way, but just keep in mind there's actually another way of doing this, which is kind of unique. But what we'll do is we'll let y = 0, so we go 0 = x - 1 squared minus 4. We'll move to the -4 to the other side, so it becomes 4 is equal to x - 1 squared. If you take the square root of both sides, you get +or -2 is equal to x - 1. Don't forget the +or -2 because that actually allows us to have two different x solutions or two different x-intercepts. Then if we move the -1 across, it becomes x is equal to +1 plus -2. So if we split this up into two values, we have 1 + 2, which is +3, and then 1 - 2, which is -1. And this sounds about right, I think. Let me just double check this calculation. Don't want to make sure that it's wrong. I think something looks kind of suspicious in this case. Might have done something wrong here. The y-intercept looks good, it's 0, -3. Oh no, sorry. The turning point is 0, -4. Don't worry. I thought it wasn't symmetrical at first, but it actually is all good. Okay, so let's just put all of our values in. X = 1, y is equal to -4 for our turning point. So that's our most negative value in this case. So we have 1, -4. Then we also have 0, -3 as our y-intercept. 0, -3. And then we have -1, 0. And then we have 3, 0 over here. Cool. So these are all of our key features. We could get all these directly or indirectly, and then we just pass our parabola through these points. And this is how you draw a parabola that's given to us in turning point form.